In this video, we're going to discuss the solutions for the midterm exam on linear algebra from the winter semester 2018. The exam contains 2 parts. In the first part, there are 5 problems, 5 questions, 4 questions, and in the second part, there are 5 problems. Let's start with the first part. The first part is about, the first question is about the vectors. So we just need to do some operations over the vectors. So if you're given the 2 vectors, if you would like to add them, you need to add these 2 vectors component wise. It is going to be 3, 6, and 9. So B transpose to the A, it's going to be the scalar multiplication of these 2 vectors. So the scalar multiplication of these 2 vectors is going to be when we multiply the corresponding components all together and sum them. So it's going to be 1 multiplied as a 2 plus 2 multiplied as a 4 plus 3 multiplied as a 6, or it's going to be 2 plus 8 plus 18, which is going to be 28. So the finding of norm of the C, it's basically just find the length of the C, which can be found by squaring each of the components of the C and taking the square root. It is going to be equal to the square root of 6. And in the last part, we need to find a unit vector in the same direction of the C. So in order to do this, we need to divide the C to its norm. So it's going to be 1 divided to the square root of 6, 1 divided to the square root of 6, 2 divided to the square root of 6. So basically the unit vector in the same direction as some vector C, it's going to be C vector divided to its norm. So the second question on the first part, it's about the operations over the matrices. If you're given the matrix C, we have to just transpose this. In this case, we'll just copy the first row as the first column. The second row is going to be copied as the second column. So now we need to multiply the A to the C transposed. It's going to be 1, 2, 1, 3, 1, 2, 4. And we have to multiply this to the transpose of the C, which is going to be 0, 1, 0, 1, 0, 3, 0. So actually we can multiply these 2 matrices in 2 different or many different ways. So one of the ways would be just multiply every row to every column and get the 4 constants to here. Or what we can do is we can try to combine the columns of the first matrix with these coefficients. So this 3 coefficients on the first row tells us that we need to multiply the first column of this matrix to the 1, the last column of this matrix to the 1, and we have to add them. It is going to be equal to the 5 and 5. And the second column of this matrix is going to tell us how we need to combine the columns of this matrix. It tells us that I have to multiply this column to the 3. It's going to be 3 and 6. So the multiplication of the 8 to the C transpose is going to be 5, 3, 5, 6. So in the last part, we need to add the A to the C, so we can do this component wise. So every component of the A matrix is going to be added to every component of the C matrix. So we're going to obtain the following matrix: 3, 1, 4, 1, 5, 4. The third question is about the rank of the matrix. So we call the rank of the matrix as the number of the pivots in the reduced row echelon form of the matrix. So if the A is given like this is already given in the reduced row echelon form, because so the first non-zero element of the first row is 1 and all the elements below are equal to the 0. And the first non-zero element of the second row, it's also here 1 and all the elements above and below are equal to the 0. So I've got a 2 pivots, so that is why rank of this matrix is going to be equal to the 2. The problem number 4 is about the dimensionality of the spaces, especially the column space and the null space, or in this case it's going to be the row space and the left null space. So the matrix has 8 rows and 11 columns, and its rank is equal to the 5. So basically, if you would draw 11 columns of this matrix, so I would assume, since the number of the pivots rank is 5, then it means that the number of the pivots is 5. It means that there are 5 pivot columns. So basically, for example, 1, 2, 3, 4, 5. There are 5 pivot columns, And in order to write down the column space, we need to combine all the independent columns and the number of the pivots. So basically the pivot columns are going to tell us where all the independent columns are located. So basically the number of the pivot columns of the matrix is the number of the independent vectors. So that is why dimension of the column space is going to be 5. And since there are 5 independent pivot columns, there is going to be 6 free columns, and the number of the free columns is going to tell you how many special solutions we have. And depending on how many special solutions we have, we can define the dimension of the null space. So the null space is going to be the span of the 6 spatial solutions, so that is why it's going to be equal to the 6. So now when we are talking about the A transpose, or the row space, so it means that I've got the 8 rows, and since the matrix has 5 pivots, it means that 5 of them have the pivots, so pivot rows basically. So that is why the row space of this matrix is going to be the linear combination of the independent rows. It is going to be equal to the 5 again, and the number of the free rows, which has 3, right? It's going to be the dimensionality of the left null space. So it's going to be 3 here. The last problem in the first part is going to be about the elimination matrices. So we need to eliminate this entry at the -2 using this pivot 1. So in order to do this, we need to do the operation R1 was the -2, and we have to add this to the second row. So we can obtain the elimination matrix from the identity matrix. If I have the identity matrix, if I apply this operation -2R1 plus the R2 to over the identity matrix, we're going to obtain the elimination matrix. It's going to be 1 0 0 -2 1 0 0 0 1. It's going to be the elimination matrix. So if I fill the numbers here, it's going to be -2 0 0 is the elimination matrix which I'm looking for. The second part of the first problem of the second part is about finding the inverse of the matrix. So first of all, we need to write down the coefficient matrix for this system of linear equations, which is going to be just the coefficients before the x1, x2, and x3 in the first equation, which are 1, 2, 3. In the second equation, they are 1, 3, 0. In the third equation, they are 2, 5, and 4. So I need to bring this matrix as a reduced echelon form, or I need to. So this part is going to be just the identity matrix. If this matrix is invertible, obviously, then the right hand side part is going to tell me what is the inverse of this matrix. So the algorithm of the Gauss-Jordan elimination works in the following way. So we choose the first non-zero element on the first row, and we're going to eliminate all the elements below this using the row elementary row operations. So we multiply the first row to the -1 and add this to the second, and we're going to obtain 1 2 3 1 0 0, and on the second row it's going to be 0 1 -3 -1 1 0. So in order to eliminate this 2, I'm going to multiply the first row to the -2. I'm going to add this to the third row, and we're going to obtain the following row. It's going to be 0 1 3 multiplied to the -2, and add that to the 4. It's going to be -2. It's going to be -2 here, 0, and 1. So once we finished with the first pivot on the first row with this one, we eliminated all the elements here, right? So now we need to go to the second row and choose the first non-zero element on this row, which is going to be 1. And I have to eliminate all the elements below this one. So we can do this by multiplying the second row to the -1 and adding this to the third one. So in this case, the first and the second row are not going to be changed. So I need to copy the first 2 rows as they are. Now I need to multiply all the entries on the second row to the -1, and I have to add this to the third row. It's going to be 0 0 1, minus 1, minus 1, and 1. Right? So we reached this, our goal, so we chose this element as a pivot and eliminated all the entries below this, right? And now we need to go to the third row. So this is the pivot, and it's going to be all the elements below this are already equal to the 0. So now we need to make the Jordan elimination, where we're going to eliminate all the elements above the pivots. So we're going to start from the last row, from the third row. So we need to multiply the pivot on the last row, 1, to the 3, and add this to the second row in order to eliminate the 3 on the second row. It's going to be row 3 multiplied to the 3 plus row 2. So in this case, please note that I'm not going to change the third row. So it's going to be 0, 1, 0, minus 4, minus 2, and 3. So now I need to multiply this 1 to the minus 3, and I have to add this to the first row. So it's going to be minus 3 r3 plus r1. So this is going to be 1, 2, 0, 4, 3, minus 3. And the last operation which is left is I need to go to the second row now, and I have to eliminate all the elements above the pivot. So I can do this by multiplying the second row to the minus 2 and adding this to the first one. Please note that in this case I'm not going to change the third row and the second row. So if I multiply all the entries on the second row to the minus 2 and I add this to the first one, what I'm going to obtain is 1, 0, 0, 12, 7, and minus 9. So this matrix is the identity matrix, and this matrix on the right is going to give me the inverse of this matrix A. So now, if we're given the system of linear equations in the form of AX is equal to the B, I can find the X by multiplying the inverse of the A to this vector B. So the inverse of the A is given as 12, 7, minus 9, minus 4, minus 2, 3, minus 1, and 1. If I multiply this as this vector B, which is 1, 0, 1, so I can multiply this as a linear combination of the columns of the first matrix. So I need to use this vector, right? It is going to tell me multiply the first row, first column of this matrix to the 1, second column of this matrix to the 0, and the third column of this matrix is a 1, right? 0, 1, 0, 1. So basically just add the first column with the third one. What we're going to obtain is 3, minus 1, and 0, which is going to be the solution for the system of linear equations. So let's consider the second problem of the second part. So in this problem, we need to find a complete solution for the system. So in order to do this, first of all, we need to start to find the reduced row echelon form of the augmented matrix, which is obtained by putting the A matrix together with the B vector. It's going to be 1, 5, and 5. Again, we're going to do the same operations as before. We choose the first non-zero element on the first row, and we're going to eliminate all the elements below this. So we can do this by multiplying the first row to the minus 2 and adding this to the second. So what we're going to obtain is 1, 3, 3, 1. So here it's going to be 0, 0, 3, and 3. Now in order to eliminate this minus 1, we're going to multiply the first row to 1, and adding this to the third row is going to eliminate this minus 1 here. It's going to be 0, 0, 6, and 6. So now I'm going to go to the second row. The first non-zero element on the second row is going to be this 3, and in order to make this pivot, I need to eliminate all the elements below this. So we can do this by multiplying the second row to the minus 2 and adding this to the third row. We're going to obtain 1, 3, 3, 1, 0, 0, 3, 3, 0, 0, 0, 0. So now this is going to be the pivot. This is going to be the pivot. All the elements of the pivots are equal to the 0. So now what we need to do is we need to eliminate all the elements above the pivot. So I can eliminate the elements above this pivot by multiplying the row 2 to the minus 1 and adding these to the first row. We're going to obtain the reduced row echelon form, it is going to be in the form of 1, 3, 0, minus 2, 0, 0, 3, 3, 0, 0, 0, 0. By the way, it would be easier for us to work with a 1 here instead of 3, so that is why we can just multiply the second row to the 1 over 3, and we're going to obtain the reduced row echelon form. It's going to be 1, 3, 0, minus 2, 0, 0, 1, 1, 0, 0, 0, 0. So this matrix became in the form of Rx is equal to the D. Rx is equal to the D. So I need to look to the matrix of the R, and I need to find the pivots. So this is going to be the pivot, and this is going to be a pivot. So the columns where there are pivots are called the pivot columns. They're going to tell us which of the columns actually are independent. And this column, the second row column, is the free column because it doesn't have the pivot. So the system has infinitely many solutions. In order to find this, first of all, we need to find the particular solution. So in order to do this, we set the free variable x2. So x2 is a free variable because the second column does not have the pivot. It's a free column. So we set the free variable to be equal to 0 and solve Rx is equal to the D. So the Rx is equal to the D is this 2 rows. It is going to be x1 plus 3x2 is equal to the minus 2. x3 is equal to 1. So if I solve this by setting x2 to be equal to the 0, what we're going to obtain is x1 is equal to the minus 2, x3 is equal to the 1. So the particular solution for the system, it's going to be minus 2, 0, and 1. So I need to enrich the solution space by finding the null space of this system. So I can find a null space by setting down x2 to be equal to the 1, the column of the 1 by 1 matrix, and by solving the system Rx is equal to the 0. So please note, in order to find a particular solution, we're solving Rx is equal to the D by setting the free variable to be 0. And in order to find the spatial solution, we're solving Rx is equal to the 0 by setting the free variable to be equal to the 1. So x1 plus 3x2 is equal to the 0 is the first equation. x3 is equal to the 0 is the second equation. So if I substitute x2 to be equal to the 1, I can obtain that x1 is equal to the minus 3, x2 is equal to the 1, and x3 is equal to the 0. It's going to be the spatial solution. And we can write down the complete solution for the system as the particular solution, minus 2, 0, 1, plus the span of the spatial solution, which is going to be minus 3, 1, 0, multiplied to some constant. For all values of this constant, this is going to be the solution. So we basically can generate infinitely many solutions by choosing different values for this constant t. The third problem of the second part is about finding the dimensionalities of the column space, the basis of the column space, and the basis of the row space of this matrix. So in order to find the column space, actually, we need to find the number of independent vectors. So basically, we need to bring this matrix 1, 1, 2, 1, 2, 2, 1, 3, 2 to the reduced row echelon form. So we multiply the first row to the minus 1 and add this to the second. We multiply the first row to the minus 1 and add this to the third row, and we're going to obtain 1, 1, 2, 0, 1, 0, 0, 2, 0. So this is going to be a pivot because we choose this and we eliminated all the elements before this. In the next step, we need to choose the second row, right? This is going to be our pivot, and I'm going to eliminate all the elements below this pivot. So in order to do this, we multiply the second row to the minus 2 and add this to the third row. And it's going to be 1, 1, 2, 0, 1, 0, 0, 0, 0. So this is the row echelon form. It is already going to tell us what is the pivot column and what is the free column. So this is the pivot and this is the pivot. So that is why these two columns are the pivot columns and the last column is the free column. Okay, so that is why the column space can be written as the span, the all possible linear combinations of the two first independent columns. It is going to be 1, 1, 1, and 1, 2, 3. The number of the vectors which we need in order to create the space is the dimension of the space. So in this case, dimension of the column space is going to be equal to the 2. And now the basis of the column space is going to be these 2 vectors. And the basis of the row space are going to be the first row and the second row, because in the reduced row echelon form, the first row and the second row have the pivots. So the basis or the row space is going to be the span of the first 2 rows. It's going to be 1, 1, 2, and 1, 2, 2. Problem number 4 is about the solvability of the system of linear equations. So basically, in the first part, we need to find a value for the a so that the system has no unique solution, fails to have the unique solution. So for what values of the a, the system fails to find a unique solution. So in order to do this, we need to write down the system of, so the coefficient matrix for the system of linear equations, which are 2, 3, 2, 6, and a. And we need to try to bring this to the reduced row echelon form by multiplying the first row to the minus 2 and adding this to the second. What we're going to obtain is it's going to be 3, 2, 0, a minus 4. So if this a minus 4 is not equal to the 0, then the system will have the 2 pivot columns. Basically, it is going to have always a unique solution. Basically, the matrix is going to be invertible matrix, the matrix is going to be non-singular matrix, and it's going to always have the unique solution. But if the a minus 4 is equal to the 0, or basically a is equal to the 4, then this matrix becomes 3, 2, 0, 0, and depending on the right hand side part, the system might have no solution, or it might have infinitely many solutions. And in the second part of this problem, so for the fixed value of the a, for example, when the a is equal to the 4, for what values of the b, the system has infinitely many solutions, okay? Because depending on what is the b, we're going to have either no solution, either infinitely many solutions. So in order to do this, we need to copy the system. It is an augmented matrix. It is going to be 3, 2, 10, and the second row is going to be 6, 4, and b. So again, we need to try to bring this matrix to the reduced row echelon form. We multiply the first row to the minus 2 and add this to the second, and we're going to obtain 3, 2, 10, 0, 0, b minus 20. So if this element here would be non-zero, then the system would have no solution. So if this b minus 20 is equal to the 0, then the augmented matrix, the reduced row echelon form of the augmented matrix, is going to be in this form. It means that there are 3 columns here. This column is going to be the 3. It means that the system is going to have infinitely many solutions. So for the value of the b is equal to the 20, the system has infinitely many solutions. The last part of this part, the last problem of the second part, is about the vector spaces. So let's say we're given a space where the vectors are obtained by adding the first 2 components. So the third component of the vectors are obtained by adding the first 2 components. So in the first part, we just need to give an example by choosing any 2 vectors from the space. For example, a v1. If I choose the first 2 part, 1 and 1, the third component of this vector is going to be equal to the 2, because I need to obtain this by summing the first 2 components. The second vector I can choose, for example, it might be 2 and 1, right? Then in this case, the third component is going to be equal to the 3. So I just need to show an example by just taking one of the linear combinations of these 2 vectors. For example, v1 multiplied to the 1, v2 multiplied to the 1 is one linear combination, right? And I need to show that this vector is also going to be along this space, or inside the space. It's going to be 3, 2, 5, and this vector is also here because the third component of this vector can be obtained by summing this first two components. So in general, I can show that this is the vector space by just solving the system of linear equations, basically. So the x3 is equal to the x1 plus x2. So as you remember previously, when I created these two vectors, I just chose any two values for the x1 and x2, and I found the x3, right? So the x1 and x2 here are the free to choose. So I can just denote them as a t1 and t2. Then in this case, all possible vectors in this space can be denoted as t1, t2, t1 plus t2. So actually I can split this vector into the two parts. All the components was a t1, it's going to be t1, 0, t1. And all the components was a t2, it's going to be 0, t2, and t2, right? Actually, if I add these two vectors, I will obtain this vector. So I can take out the t1 from the brackets, it's going to be 1, 0, 1. And it can be written multiplied as a t1 plus 0, 1, 1 plus t2. So actually, this is the equation, the vector equation of the plane through the origin. And we know that any plane through the origin is the vector space. So this is the proof how to show in general that the vector space, this V is the vector space.